So I did my PhD in math, algebraic geometry, and statistical learning theory, in fact, singular learning theory. Over time, I became very interested in spiking neural networks. And in fact, over the last 10 years, I've been working on that as well as program synthesis. I tried to do a startup back in 2017 around this topic. The reason it didn't work out was that language models at the time weren't very powerful. But I can talk more about that after the talk if you're interested. So now we here at the Topos Institute, we are interested in how we can change the way that we model our world and how we come to make sense of the world and how we make decisions. I'll talk more about that in a bit. And the work that I'm presenting today is joint work with Atlas Computing. And in fact, we are coming up with a concrete roadmap towards formal AI-assisted code specification and synthesis. And the goal of that is to build safer and more secure social technical systems. And the reason we're working on this roadmap is that today we are seeing language models becoming more powerful. In fact, in February this year, Microsoft and OpenAI, they announced that they found accounts on ChatGPT accounts of hackers that were trying to use the platform to improve their cyber attacks for scripting, for doing research on different attack strategies. And the question is, as these malicious actors become better at what they do through using these kinds of tools, what can we do to protect our social technical systems? So it's not just intentional attacks that we're worried about, we're also worried about accidental mistakes. So like, for instance, someone forgets to make some mistake in their protocol, which an example I'll talk about later. Those mistakes and protocols might lead to very serious effects on our society. I'm also interested, I mean, the example that I gave was human-led, but you can also imagine that in a scenario where we have autonomous AI systems, they might be the ones leading the attack. And the question is, to some extent, does it really matter if they're being led by humans or by AI agents? At the end of the day, it is the social technical systems that we're trying to protect. And we want to protect our systems against the strongest possible adversary. And so the challenge is that we want to harden our systems, and we want to do this with formal verification. Why formal verification? So if we don't do formal verification, we might find ourselves fixing our social technical systems one bug at a time. And so the example that I give here is from the 2014 OpenSSL heartbleed bug. So heartbleed is a play on the word heartbeat. There was a protocol in OpenSSL where they tried to find out if the server is still alive. So to check the heartbeat of the server. And in that protocol, there's a part where you can specify how many letters or how many bytes you should have in your response, the server's response. And it turns out that people could use that to extract more information from the memory of the server than they are allowed to. I mean, this is a very trivial bug. It could be solved quite easily by putting some checks in place, but someone made a mistake and it was discovered and it was quickly patched. But if we had adversaries out there, maybe a very smart human with a very smart AI system helping him, he might be able to exploit that bug to attack our social technical systems, especially if many of them are built on top of a basic protocol like OpenSSL. Now, formal verification, I think some of you are familiar with. It's a very powerful technique for hardening our systems. And a good example of that is ComCert. So ComCert is a certified C++ C compiler, certified C compiler. And in 2011, an experiment was done to check the vulnerabilities of many different C compilers out there. And this is what the author said about ComCert. They said that ComCert is the only compiler we have tested for which CSmith cannot find wrong code errors. And this is not for lack of trying. We have devoted about 6 CPU years to the task. So they basically attacked the ComCert compiler with 6 CPU years of computations. And even after that, they were not able to find any bugs in the system. Now, we want to have formally verified systems, but these systems are very, very hard to implement and create. So here at the bottom, you see a picture of the concert compiler and all the different languages, intermediate languages are involved, and all the intermediate verifications have to be checked in the translation from one of the languages to the next. And we really don't expect normal human beings who don't know much about mathematical theorem proving to be able to build a system like this. So writing formal specifications, implementations, and proofs is hard. There is, we want to harden our systems, but formal verification is not for anybody. Now, we do know that large language models are getting good at generating code. So here's an example of a GitHub Copilot. So in the Copilot, you could use your, go into VS Code, you can write down a command, which is in green, what you want the code to accomplish. And sometimes the Copilot will give a piece of ghost text that suggests what code you could write to accomplish that. And my friends who have been using this says that it's actually quite good for simple tasks. Now, the question is whether, so I talked about how we could be facing a world where we're being attacked by humans using AI-enabled technologies. Question is whether we can defend ourselves against that with also AI-enabled technologies. How do we ensure that, so if we're going to use AI-enabled technologies to write code, how do you ensure that the code that they write is actually correct? How do you ensure that's not hallucinating something that has maybe even more bugs than a human programmer would produce? And how would we go about doing that in a scalable way? And so that's kind of the crux of this roadmap project that we have with Atlas. And here's we're still in the middle of writing up this roadmap, but here are some of the projects that we've identified for the roadmap. And the skeleton of the roadmap is this workflow that you see over here. And those who are familiar with Davidat's Safeguarded AI program might recognize this workflow. In this workflow, the first step is to model the world. After that, you would then write down your specifications in terms of your world model. Then you would generate an implementation or a proof that satisfies that specification. You would then do a review of that code, checking the proof is correct. And usually this review is done with a very small trusted kernel. So you don't have to actually verify all the steps before. You just have to verify the proof that was generated. And then lastly, you would deploy that piece of code in your systems. And throughout all this, we have users which are interacting with the system at different stages of this workflow. So for instance, the users might say, okay, so the AI system may have generated a specification at this step, and the user could say, that's not what I want. What I actually want is something else. And over time, iteratively, you imagine the AI system becoming better at generating the right specifications. So I'm going to talk about, dive into some of the projects that you see here. Yes, this question.
Yeah, maybe this is a good time to.
Well, you can just leave it in there and
Okay.
probably pick you up.
Great. I'm curious how well LLMs are doing at writing proofs these days.
Good question. So I have some video demos, video recordings of demos that I did with ChatGPT, and we'll take a look at that in a bit. Okay, so I don't have time to go through all the different work packages, projects in the roadmap, but I want to highlight a few ones which I feel that I think are important. So let's talk about modeling. So one of the things that makes AI-assisted formal verification different from just traditional formal verification is actually the fact that you need training data for the AI models. And this is where legacy code and legacy documentation become very important. In traditional formal verification, you might not care so much about legacy code. You just want to write everything from scratch and in a way that's correct. But in doing AI-assisted formal verification, the old legacy codes, legacy documentations, they will give some kind of indication to the AI system, the kinds of specifications that you want to write and the kinds of code that you want to write. Maybe there could be different versions of code that you write, but one of them is more efficient than the others. So the legacy code would be able to help us find that efficient code. Also in any formal verification system, you have to specify what language you're using for describing your model. And so as we start to verify different kinds of systems out there beyond C compilers, it becomes very important for us to study the kinds of specification languages that we could use, and how to design them in a scalable way. So one of the things that is not included in this roadmap is something that we call world modeling or collective modeling. Okay, world modeling features very prominently in Davidat's Safeguarded AI program. It is also something that we are focused a lot here in Topos, and so I just want to talk about that a little bit, because to some extent, the roadmap that I'm describing today sits on top of our ability to do world modeling. And so when we think about world modeling, we are thinking about a collection of models. We're not just thinking about one model for everything, nor are we thinking about many different models by sitting on top of a shared domain-specific logic. But we are thinking about possibly many different kinds of logics out there, and different models sitting on top of those logics, but somehow there has to be some interconnection between these models for us to have a sense of the tasks that we are trying to solve. So some tasks that we solve could be based on several of these different models. So we need a way to translate between these models. And so the way that I like to think about it is that we have some kind of a fabric. This fabric has models attached to it, and one dimension of the fabric is logics, different kind of logics that you have. And the other dimension of the fabric is the kind of versions that we have of those logics. So over time, we expect our logics to evolve. And so we need to think about how they depend on each other as they evolve. And we also think about what kinds of properties these models should have in order to be effective. And so one aspect is that these models have to be formal in the sense that you should be able to check if they're correct. At the same time, they have to be conceptual in the sense that humans should be able to understand that. So the humans may not understand the formal syntactic form of those models, but they may understand maybe a visual form or a graphical form of the model. And they will use that to check their understanding of the model. And the last thing is that these models should be interoperable between different logics and between different versions. And if I were to take this step of modeling and go even deeper, I think we have to understand that as we build this roadmap for defending ourselves against possibly like AI attacks, making our social technical systems more secure, one of the assumptions that we are making is that in the short run, one assumption that we're making is that in the long run, we want to build models which are collective and which helps us to, as a community, as a society, to make sense of the world around us. And this is as opposed to more a top-down decision-making kind of structure in the society. So, for instance, if in our society today, many of our structures are top-down, whether you're trying to decide who to hire or whether to decide what kind of policies to implement on a society level, you have a lot of these top-down structures, and it's understandable that we would worry that maybe a very strong AI agent would come along and find that the best way to attack the entire society is to exploit one of these top-down structures and to use that to change the way people are hired or to put different kinds of people in government. And if that is the attack approach of an AI agent, then it makes sense that the goal is to build aligned AI models. I think we are arguing that a better long-term solution is to rebuild society that has a high value for collective sense-making. That we want to create structures where it's easy for humans to come together collectively and not just collectively make a decision, but to collectively say, we don't actually understand what's going on. We need to make sense of the world that's changing around us. We need to come to a way that we could achieve maybe some kind of local consensus, and then use that to build actionable systems on top of that. And so And so when we're talking about building a roadmap for AI-assisted formal verification, we are assuming that in the long run, there is a way to collectively come up with with our world models, and that from that we could formally verify and protect our social technical systems in a way that respects those world models. So this is a prerequisite for the roadmap, but it's not actually something that I'm going to dive too deeply into. We don't have projects around this, but this task is being looked into by people at Topos, but also people at ARIA in WDOT's Safeguard.AI program. So that kind of brings me to the next aspect, which is how you could, how you want to design the interaction between the human, the AI, and the proof assistant. So I was talking about collective sense making. So the model of interaction that we are having is one where we have artifacts which are clear to everybody, and that people could make questions about it. People could make suggestions on how to improve it, and we want to build some kind of a system that puts the humans at the center of it, while providing assistance both from the formal side through a form of proof assistant, but also having smaller AI models that perhaps could assist in different steps of the workflow. In the short run, in this roadmap, we're thinking about building a proof assistant that integrates with existing technologies around formal verification, such as Lean, Pharmacy, or Varus. Varus is actually a formal language for Rust. But in the long run, we could ask ourselves whether we can redefine what a proof assistant is in the first place. Does it have to be built on top of dependent type theory? Does it have to be some kind of a input-output system, or could it be something much more general than that? And this is something that people at Topos are thinking about, but is not a part of this more short-term roadmap. And we also want to be able to, I talked about having different kinds of logics. We also want to be able to translate between different kinds of logics. So example would be that one of the logics that a lot of people like use in formal verification is COP. And more recently, Lean has become a more popular language. And the question is, can you take things that were created in COP, lots and lots of work around formal verification in COP, can we translate that over to Lean? And it turns out that with you can actually even use ChatGPT to do part of that translation. So I gave this prompt to ChatGPT, translate the following code from COP to Lean, and it turns out that it correctly gave me the right translation in Lean, and on top of that, it created additional logical structures that would make this translation correct. So I was very impressed with how ChatGPT did this translation here, and I think just to answer one of the questions earlier, we can use these GPT systems to do logic translation. This is a question?
Do I need to turn this on or anything?
No, should be good to go.
It's just a quick question. Like, how do you verify that it did the translation correctly? Is there a way to just check the specifications line up somehow formally, or do you have to like look at it yourself and make sure that it represents?
So that's a very good question. Like, just say I copied this into Lean and I ran it, and it ran it without any errors. It doesn't mean that it's actually correct. It could just be that here I'm asking for some kind of a denotational function, but maybe here it instead gives me a way to add two numbers together. And to do that, you could think about, you have to go beyond GPT. You actually have to think about the grammatical structures, the logical structures of the two logics, and then you have to think about how you could do that translation in a way that is faithful to the logical structures, and that for that you could do something like, say, category theory, and to think about how this translation is actually a functor between two different categories. And you can express this also as another model in the system for doing this correctly. But I think you definitely will require some kind of human, at this point, some kind of human handholding to make sure that this translation is correct.
Oh yeah, there's actually a mic behind you. I should point that out. Whichever's easier.
Cool, no worries, thank you. Yeah, related question, just, you know, I'm not a person who does program verification, but I wonder if you could automatize making tests rather than proofs. So you have a test suite, it runs both code, and then if they match in terms of the outputs, maybe there's some like informal way, and that might be easier
Yes.
to write automatically. I'm
Hmm.
curious.
That's a very good question. Yeah, I've seen examples of GPT actually creating tests, unit tests from the code. So we know that's possible. In a short term, to provide some kind of, it wouldn't be a full formal verification, but the unit tests do provide some kind of guarantees. And one of the projects that I'm in discussion with some collaborators is how we could turn those unit tests into actually formal specification. So for instance, if the test was saying like, okay, I want to test if the sort algorithm is doing the right thing, I would be checking consecutive elements of the sorted list of the output to make sure that they are in the right order. If that was my unit test, then the specification that we could get GPT to create for us would be to actually check that for all elements in the list, you have the order relation. So yeah, I think there could be a two-step process where we first get GPT to create unit tests and then again use GPT to create specifications from the unit tests. Okay, so I'm going to talk about the third step of the workflow, which is about specifying, generating specifications for our codes. And so I told you that I did a startup back in 2017 about program synthesis. It turns out it wasn't actually hard to write proofs using an AI model. You could run some kind of a Monte Carlo tree search to look for proofs in the space of proofs. But the hardest part was actually translating the human language, human intent into something that was formally verified. Like if you have like we expect most people do not know existential quantifiers like or universal quantifiers, and how would then, if you don't get this first step of having the specification, you can't actually expect the rest of the synthesis, program synthesis to run if you don't have that. Back then, the language models were quite bad at translating human language to formal specifications, but today GPT does that quite well. I'm going to show you an example. And here in this example, I asked GPT to write down the factorial function and then go on to prove that the factorial function produces positive integers. This is completely natural language. What GPT is about to do is then firstly write code, formal code for the factorial function. So it understands what factorial means. There's some inherent training data that teaches them that. But it also goes on to write down the specification that this factorial function is always positive in the correct way. And it actually outperforms itself by going beyond that and actually proving that this is in fact true. So it creates this proof here, which is a technical proof in Lean, and you can actually run this in Lean version 3 and it runs correctly. Okay, and I tried running that in Lean version 4, it doesn't work. So GPT-4 is still trained on the last version of Lean. This is something that we have to worry about if you're going to use like AI systems to do to generate code and things like that. Versioning is going to be important. But yeah, so the real challenge here is that as a stochastic parrot, all right, language models, they don't necessarily understand what it means for a term or a program that it generates to be well formed. So it is still an open problem on how you could maybe create AI models that can do this in a better way. So for instance, given a grammar for your DSL, how could you then turn it maybe more into like let's see, how can you then construct a term in that grammar in a much more like tree-like way, as opposed to having to keep track of the number of parentheses and brackets you have along the way. But yeah, I go too much into details, but that's one of the problems that is still yet solved. In fact, sorry, this video is. In fact, you can GPT is also quite good at creating specifications from legacy code. So you give it a piece of code, you don't actually tell GPT what the code is doing, and you ask it to try to figure out what was the specification that this piece of code is trying to satisfy. And so here in this demo here, we are working over the Daphne language. So Daphne is a one of the languages for low-level formal verification. And I tell GPT that it is an expert in Daphne, and I'm going to give it a piece of Daphne code, and it's supposed to find out the weakest precondition and strongest post conditions, as well as something called loop invariance that has to be satisfied by the code. So it basically means, what is this code doing? Give it in formal terms. So it has to take my code and replace the to-fill string that you see here with actual specifications. And you see here, Daphne analyzes the function, which is called max array, and it figures out it is to find the maximum of a list of elements, right? And then it goes on to figure out that the precondition is that the list must be non-empty. It must have that your maximum term must be bigger than everything in your list, and your maximum term must also be one of the elements in your list. And so it actually answers the question correctly. So some of you may be wondering, maybe I gave too much away by calling my function max array. So it figured out that it's trying to find the maximum of the array from the name of the function. I did another experiment, which is not here, where I replaced the word max array with f. And then it goes on to say, your function is trying to find the maximum of a list. So at least for simple examples, maybe it, based on its training data, is able to figure out what the code is trying to do. Okay. And now I get to my favorite part of this talk, which is about how we can, from a specification, generate a proof or generate an implementation of that specification. So before I talk about generating code, I need to tell you that there are two broad categories of logics out there that we use for informal verification. The first kind, they are called decidable first order theories. So they are based on logics like OR logic or separation logic. And in these kinds of logics, you specify what the inputs set assumptions about your input, and then some conditions about what the output should be. And then you also have some basic building blocks for code, like maybe some memory management stuff, some assignment of variables, maybe some some arithmetic, things like that. But the codes are usually not more complicated than that. And in those examples, your software is actually able to check in finite time if the implementation satisfies the conditions that you gave it in the first place. So those kinds of systems are called automated theorem provers, or ATPs. And examples of that would be like Daphne, Pharmacy, or Verus. In these systems, applying AI to solve the problems is actually quite straightforward, right? You get the AI to generate the implementation, like what we see here for finding the maximum of the list. And then the proof assistant, the software actually takes care of everything else. It does the type checking, it does the check for correctness, and it tells you at the end of the day, is it right, is it wrong, and where's the error, and so on. It might even sometimes give you a counterexample. So that's this kind of generation is not what I'm interested in. I'm actually interested in a different kind, a more difficult problem of code generation, and that is over logics which are expressive and higher order. And an example of such a logic is dependent type theory, right? In the dependent type theory, you could write down functions where the output type depends on the input you give those functions. Okay, and because theorem proving is so difficult over these kinds of higher order theories, you actually need humans to come in and give instructions on how they should proceed on the proof. And so these kinds of software platforms, they're called interactive theorem provers, or ITPs. And examples of that would be Cop, Mean, and Agda. So here's an example of the proof I showed earlier for the factorial function. Here you can, the logic is so expressive, you could write down mathematical properties of the functions you're writing. And for instance, this would be really hard to do in Python or Java or C. Now, to solve the problem of code generation, code synthesis for these expressive higher order functions, one of the most successful methods is called refinement-based synthesis. Okay, it's been around for almost 50 years, but it's an active area of research. In refinement-based synthesis, you start out with with maybe a very broad specification of what you want the output to be. And through many different steps of refinement, you narrow down what you expect the output to be by adding more properties to the output. And finally, you end up with the situation where the output type has only one element, and turns out that one element is a piece of code that produces the output that you want. And so, so with this method of synthesis, you can actually produce functions which are not just functional or correct. You could actually get code which is performant or very efficient, right? So an example would be the Fiat crypto library from MIT, Adam Shepardler's group. And today, it's estimated that more than 95% of HTTPS connections by browsers actually run the algorithm that's generated by refinement in his library. So there's so not only do we get code that's correct, we get code that's efficient. So we know that this is how we want to generate code for our specifications. The question is, how do we then use AI assistants to do that? And before I talk about that, first, I want to show you that when you generate the code that you had on the previous slide, here, where you see the refinement happen in different steps, the thing that's driving each step of the refinement is something called tactic. So in the ITP or in the proof assistant, by writing down tactics, you can simplify the specification that you have. And what you get at the end of the day is not just an implementation, but actually a piece of proof that this implementation you've derived satisfies the original specification. And then you often need one extra step at the end to extract the implementation from the proof. So you get a proof that carries some kind of implementation or code, and then you have to extract the code from the proof. So the first insight about using AI assistance for that is that we should be generating our proofs of code tactic by tactic and not token by token. So in the example where you saw earlier where I had ChatGPT write down the factorial function, it was actually generating it token by token, word by word. But the question is whether there is a way to generate that code through a series of program changes or program transformations. All right. And the second thing is that the second insight is that if you want to use AI models to generate tactics, you want those tactics that you're using to be generic. In other words, the tactics need to not just work for a very specific class of problems, but it needs to be able to work on many different kinds of problems out there, but sharing maybe some kind of similar structure. And the way that we could find similar structure across different programming problems is to use something called category theory. So category theory is the mathematics of finding similar structure, finding isomorphism between structures. And if we have a more categorical view of defining tactics, we then could come out with a family of tactics that we could then train AI systems to be able to use very well for generating code. And in fact, there's great reason for us to believe that this will work, because about 2 decades ago, we saw for the first time a formal proof of the four-color theorem, as well as the odd-order theorem in group theory. And those were actually accomplished by this kind of categorical method, where you look for similar structures, you extract them out in the form of type classes in your proof assistant, and then you run tactics that respect those type classes in a very generic way. So if you want to read more about this strategy here, I highly recommend a book called Mathematical Components. And in that book, you will find, for instance, a strategy for dealing with equalities, right? So we know that, well, equality is one of the most mystical things in mathematics. Equalities and numbers is easy to talk about, but when you talk about more general things like quotient types and things like that, equalities become difficult. And the question is how you could design something like a rewrite tactic or rewrite rule to work across all these different kinds of equalities. And that's exactly what they did for these proofs and in this book. And so the thing is that we want to do the same for code synthesis, what was done for the four-color theorem and odd-order theorem. So coming to the end of my time, I think I will just briefly show that We also, in our roadmap, think about something called program equivalence, when to check if two programs have the same behavior. And we also talk about proof repair, where if you update the specification, how you use an AI model to then repair the proof, the old proof of the theorem into the new one for the new theorem. Okay, so in summary, right, we want to scale formal verification with AI assistance. What are some of the tools for that? The first is that we want to use legacy code and we want to train our AI models with that. The second is that we want to build a much more effective interactive tool for coding in the same way that we've done for theorem proving. Third, we want to think about ways to change convert natural language specifications to formal structures. And lastly, we want to generate code by construction and not by sampling or token generation. Okay, that's it. Yeah, thank you. Any questions? Yes.
I have two. One is just like a newbie question of, suppose I'm like writing a proof for a math class, like linear algebra class or something. What like style of proof am I writing in that case? I think you had the different.
Oh, I see. If you're writing a proof in a linear algebra class, what style it would so for instance, let me see if I'm understanding your question correctly. You could use something like, you could use, suppose you want to use dependent type theory, then you could go into the Lean theorem prover. You could write down the theorem that you want to prove, which is that, okay, if I have if I have a linear map and the rank of the linear map is n, and then the co-rank is m, then n plus m is equal to the dimension of the square matrix or something like that. Then you could go through a series of tactics that would maybe expand like computations of the rank and co-rank and verify that it actually gives you the answer that you care about. So that's one way to go about proving something like that. There's another way of proving a theorem in linear algebra, which is to use something called graphical linear algebra. Is that right, Brendan? And in that case, you actually write down these matrices as the maps, these linear maps as edges on some graph where the nodes are actually vector spaces with different dimensions. And this is based on using category theory to represent these maps. And you could, I think you can go further and actually talk about dimensions and ranks and co-ranks using this language and eventually come out with a graphical proof of that theorem. But that's not something that is you can do. That's not something that you can do right now in Lean. You will need a different kind of theorem prover for that. And the question is whether we could build something like that more in general.
Cool. And then my second question is, it seems like you need a pretty powerful AI to write the proofs. So how do you align that?
How do you align that? Align the AI
Like,
model.
does that one need to be provably safe, or how does that work?
So that's a good question. First of all, in my own experiments, I found that we don't actually need very powerful language models to do code synthesis. You could train a reinforcement learning model, a small one. It doesn't have to have like billions of edges or things like that. It turns out that they already do quite well. It's the part where you have to translate natural language to formal proofs that I think you can't really run away from the language models, because you have to train it on all of, you have to train the model to understand English or other languages, and so you get big models out of that. The question then is whether we are creating another problem, right? I'm checking if I understand the question correctly. As we try to build safer social technical systems, we are using AI models which in themselves are very big and they could present certain risks. And I would say that in my initial assumption, I see my initial assumption for all this to work. There are two parts. The first part is that if I formally verify my software systems to have certain guarantees against code injections and things like that, I create a larger social technical system that's safe from both AI human-led attacks or maybe AI agent-led attacks. So even if my system ends up using models which are very powerful, that model in itself would not be able to break the system that is proven, that is generated with the right proofs. Okay, because those proofs are not checked by another AI system. It's actually checked by a proof checker, which is a very small kernel that humans can actually check and make sure it's correct. So we have some guarantee there so say you have in human terms, if you have a genius that created a very good cryptographic system, can he break his own cryptographic system? And the answer is not if the cryptographic system has very strong formal mathematical guarantees. The second point assumption that I'm making is that we want to move away from these large top-down decision-making structures. Top-down decision-making structures are causing us to build causing us to have incentives for building monolithic AI systems. If we could create better tools for collective sense-making, I think the incentives for creating these monolithic AI systems could go away. We end up with smaller AI systems that can help us in different stages of the collective sense-making, and we de-risk we de-risk the system by removing incentives for having these large AI models. It's not as strong a guarantee as in providing formal proofs, but I think it's something.
We just talk about it. Yeah. Okay. So okay, here's one part of the formal verification theory of change that I don't understand. It seems very difficult to me. Right? At some point, we want to include probabilities. The world's probabilistic, right? And we probably want to relax our guarantees to be probabilistic guarantees, not universal guarantees. Right? It's like it's not possible to make sure that the system's safe for all possible inputs, but 99.99999% of the time, we know that it's going to be safe. But okay, you come from an SLP background.
Yeah.
Sampling from posteriors when they're singular and they're going to be singular is hard. It's very, very hard.
Right.
I don't understand how we end up with any kind of tight bounds as soon as we jump into the probabilistic regime.
Yeah, that's a very good question. I still think about that. I don't have a good answer. The talk that I've given today addresses more of the simple kinds of formal verification issues that we have out there, like making sure that your protocol doesn't have a way to extract more than it's allowed, more than certain number of bits from the memory than it's allowed to, or like to have certain kinds of guarantees on permissions and maybe other kinds of cryptographic guarantees. When we come to now deal with probabilities, I think it really depends on the kind of guarantees that you want to have about those systems, and you have to be careful that having a specification that says something like, okay, we have a 99% probability of this being wrong, this being correct. Is that actually what we want? It sounds like it would be what we want, but maybe that 1% of error is enough to create havoc for you, and so that's actually not what you want. And then you have to go back and think further about what actually it is that you want to have in your system. So I haven't really answered your question. I do think it is a hard question. I think even for humans trying to prove guarantees about probabilities, especially tail end probabilities, finding so making assertions about posteriors, for instance, those are hard problems. I'm not even sure if AI is anywhere close to being able to provide proofs of those things automatically. I think just to say that the program described here still kind of works for the basic problems, but for the more difficult problems, I think it's something that we should be thinking about.
Are you referring to proving properties about the AI system itself and internally, or AI's properties about the AI system's impact with respect to a world model?
I think it's mostly the second one. With respect to
okay.
Yeah.
So, yeah, so one picture there, then it's just like, what language do we have, or what they have, what sort of expressions, what's legible for the world model, and what sort of expression we can improve in that language. I agree, it's a solid point, an important point of this thesis, and we should talk more.
Oh, yes.
Can you use the wireless mic behind you? Might be easier, and feel free to pass that around in the back.
Thanks. Yeah, thinking about this from like a kind of red teaming perspective, or like a failure mode perspective, where would you say is the sort of the weak point adversarially in this process? If we think that the AI systems might be trying to deceive us, it seems like once you have the formal specification, because you've got these automated theorem provers, my understanding is that is all sort of very ironclad. And if you were to think what's the weak point, it would be translating from natural language to formal specification.
You're exactly right.
Okay.
That is where I think the big point is.
Is there any way to sort of get to defend that in some way, to convince yourself that this is, you can trust your AI model to write this really long, complicated formal specification that is hard to check all the details of?
Yeah, I think there will always be a risk there. You can't make that risk go away because there's no way to formally verify that the natural language input that you have is somehow complete, and then you have to define what complete means. It's another specification again. What we can do is, as a society, come up with security templates or specification templates. So we could have experts out there which say, what does it mean for a web page to be secure? And don't leave the decisions of what it means for web pages to be secure to everyday users who may not know much about security. And as these templates come out, they could be specifications that normal everyday users could download and say, I want the system to check if my web page satisfies this security specification that were written by experts. And over time, you expect these specifications to be improved, to get better at covering all the edge cases that were not thought about. So until that day happens, there will always be holes that AI systems could exploit, I guess. And then it comes to the question of how we could collectively, as a society, come up with these kinds of standards or make sense of these kinds of standards. And then I think the highest rate of success would be to empower humanity with these kind of collective sense-making tools.
Right now this is a roadmap. Are you intending to build like prototype tooling for it? And then second, if so, do you envision like a specific group being the initial ones to like adopt these practices?
That's a very good question. We are still in discussion about precisely those questions. In fact, it's evolving every day. So one of the things that we are intentionally doing in this roadmap is to come up with more concrete near-term projects that we can do instead of like laying out the 10-year, 20-year plan. Just because not only is that because the 10-year, 20-year plans are difficult, but also it's hard to predict where things will be after 5 years. In terms of the short-term plans, I think both Topos and Atlas have some projects that we want to go into in fulfilling parts of this roadmap. But we're also looking at we are talking to our partners from different national labs. They are also quite interested in this roadmap. Yeah, so that was your first question about implementation. And then there's the second part of your question, which was the users. I think we are at least the obvious users right now are people who need cryptographic guarantees. We are also talking to some of our collaborators who work with like cyber physical infrastructure like power stations or electric power grids. And the kinds of systems that they want to verify there. There are some involving autonomous vehicles and the protocols they use for talking between them and how we can secure the protocols there. But I would gladly welcome any ideas about potential users of this system who want to test such a system with us. Yeah.
We have time for one more question. If anybody in the room or online? You mentioned part of the idea of your group focus and maybe Alice is to empower maybe more decentralized local decision making. Are there any work in the group on these either protocols or is this social choice theory? Is this extensions to this? Is this something different? What can you say about that work?
Yeah, that's a good question. I wonder if I should ask Brendan if he has any thoughts on that. Yeah.
Yes, there is work. It's still early stage. So in a bunch of various directions, I think things like social choice theory or sort of formal methods are interesting tools. And for example, we'll be contributing to the S process and understanding the mathematical basis of that algorithm and re-implementing it. And we'll do some of that sort of work. And then we're interested in sort of tooling around how you elicit. In some sense, it's a question about specifications and natural language. No natural language statement is really a specification, right? It's not precise enough to actually be something that is sort of formal mathematical. But what it is a way to elicit a specification, and that thing happens by dialogue. So the question is, how do you provide good tools for eliciting exact specifications? And they look like it's not so exotic, right? They look like things like Google Docs or Google Sheets or something like that, but with more and more structured parts. So some more formal parts of the system are legible to the mediated artifact, hence to the people using it. So we're being implementing in the beginning. So this model part of Shaowei's roadmap, part of that is being implemented through like just a web app for collaborative specification models. And then beyond that, the question is what is the cultural use like of this? Like how do people have good discussions with these mediated artifacts at the center so they get to agreement and trust and a robust specification of what people actually intend, which is the ultimate question of specification. How do we know that what we put into the specification is actually what we intend? And that's there's a software aspect to that too, which is just how do you hold good meetings. So all three aspects of things we work on.
Yeah. So that aspect's not really covered by the roadmap, but there are different groups of people out there thinking actively about this.
One more round of applause for Shaowei.
Thanks.